Please welcome to the ATT&CKcon stage, Adam and Jesse. Your scepter.
Thank you. There we go. There we go. All right. Hi, everyone. So we are here to talk about validating attack technique coverage using EDR telemetry. And there will be lots of AI-generated canaries throughout the talk. So I'm Adam Ostrich.
I'm Jesse Brown.
And we are both senior detection validation engineers at Red Canary. The detection validation team is more of like a research engineering or research and development type of team. We have a combination of cybersecurity and software engineering skill sets. And our charge is to understand how things should work, make sure things work like they should, and then make things work better. It is a very vague kind of task that sort of has broad-reaching consequences across the company, but sort of motivates why we are very interested in validating that EDR telemetry works for our platform. So to start off, we're going to talk about what is EDR telemetry, make sure everyone's on the same page, up to speed, sort of talk about how we think about it. We're going to talk about how Red Canary works and why validating EDR telemetry is important for us. We're going to talk about validation of attack techniques. I want to thank Adam Pennington for teeing this up very nicely in his talk earlier. So what we do is we take our attack techniques, we break them down to their base data components. Then we use that to sort of do broad coverage validation, to sort of recombine them and do lots and lots of different techniques with sort of a subset of data. We're going to talk about our automated validation workflow we've put together. So how I've been able to scale this with a whole lot of tooling to make it a lot easier to run, test, and analyze things. Then talk about some lessons learned, some things that we thought were interesting we wanted to share with the community. So first, what is EDR telemetry, right? Make sure everyone's on the same page. So at its basic level, EDR telemetry is just a representation of behavior on the operating system for security purposes, so you can see if a bad thing happened, right? EDR, or Endpoint Detection Response, there's a lot of different pieces to it, but the main ones that I care about is that you have a sensor that sits on an endpoint that when it thinks a bad thing happened, it'll generate an alert. It'll also generate EDR telemetry that streams up to some sort of cloud portal that you can use for threat hunting. The reason why EDR telemetry exists, I think, is this is how I think of EDR telemetry and why it's interesting. So back in the day, forensic images were really important when you think a bad thing happened, right? You had to go in, you had to dump everything on a computer, dump everything in process memory, dump everything on the hard drive, right? And this gave you a very large and very complete haystack in which you're trying to find a needle. The problem is that the cost of collection is really high. It takes a lot of time, takes a lot of compute cycles to get this data. And what people found is that you can actually do most of your hunting with a much smaller subset of that data. And with that smaller subset, now the cost of collection goes way, way down. So you kind of have this balance to get EDR telemetry of balancing the signal to noise ratio of what you're grabbing. This makes EDR telemetry very interesting to study because by definition, you are filtering things out and cutting things out. And so it's really important to understand where those edge cases are. All right, so another way of talking about EDR telemetry, I want to go over some of the types of telemetry you'll see. And I'm using the same LSAS dumping example that Adam also mentioned. So here we have a remote PowerShell connection. And to run this PowerShell command line, which is just going to run proc dump to dump LSAS to get credentials. And so we have the initial remote PowerShell connection into the computer. So connection to WSM prov host, you'll get network connection telemetry. When PowerShell actually launches proc dump, you'll get a script load to see not just that proc dump ran, but also this invoke expression command. And then you'll get a process start telemetry to see that procdump.exe was actually launched. When it starts loading DLLs into memory, you're going to get module load telemetry. We have to accept the EULA. You have to modify the Windows registry, so you get registry modification telemetry. And then you get your actual cross-proc, so you're accessing LSAS's memory space, so you get a cross-proc or cross-process event. And then finally, you're going to take that data and you're going to dump it to disk, and you get file create telemetry. So you get a lot of different types of behavior from this type of technique, but there are certain blind spots that you're getting in EDR telemetry. The first is depth of information. So a good example here are system APIs. So, right, I believe procdump is calling certain APIs inside of kernel 32.dll to access LSAS's memory, grab all the data. You don't see that level of detail. You just see that the thing happened. And so a lot of sort of more traditional behavioral signatures aren't necessarily going to work with EDR telemetry. There's also certain types of actions you're not going to see. A good example is file open telemetry, which is very noisy and therefore very highly filtered if you ever see it at all. And this is just because, if you're in Windows, you open up a directory, there's 1,000 files in there. Well, guess what? If you open an Explorer, you're now going to generate 1,000 pieces of file open telemetry, right? So it's not a very high quality signal, but there are times when it's useful that I'll talk more about later. And right, just at a very, very basic level, it's nothing fancy. It's just JSON. It's a bunch of flat text with key value pairs to give you sort of the metadata around what happened. So here we have a process start event, and this is just saying what the command line is, hash, name, path, PID. An actual example has a lot more data, but this is the level of data that we are looking at in EDR telemetry. And now Jesse is going to talk about how we use EDR telemetry to perform detections of red canary.
Thanks, Adam. So yeah, maybe before we get started here, I do want to make my stance publicly known on this whole MSHTA debate. Sorry, Adam and Katie. Also, I would like to cast my vote for dumpster diving's addition into attack, just because I want to write the Atomic Red Team test for that. So anyways, as Adam just described, EDR telemetry is JSON usually, and usually it's a lot of JSON. So Red Canary, and I imagine many of you too, have built data processing pipelines to handle this telemetry. But like, why am I talking about a data processing pipeline right now? Well, by understanding your data processing pipeline, you can figure out windows into that pipeline where you can insert validation. So this is a high-level overview of our pipeline. On the left, you have various data sources feeding into a standardization phase. This is essentially mapping disparate data sources into a common model. In the open source community, there's standards like Elastic's common schema or Splunk's common event format. This gives your detection analytics the ability to operate on those standardized models. Those detection analytics create alerts or tip-offs. At Red Canary, we call our own internal alerts tip-offs. And then those get fed into a portal or like an analyst workbench where your detection engineers, threat hunters respond to threats. So we'd like to kind of suggest that there's two great places to inject some validation. One is right around that standardization phase where you get to validate data components. And then the next stage being right after your detection analytics where you can validate they're actually working as expected. So let's double click into standardization. It's a really simple way of saying that we're just mapping input fields to that common model. Yeah, and at this point, you're probably asking yourself, like, what does this have to do with attack? Well, like, these are data components. So data components being one of my favorite recent additions to attack. Essentially, like, I think about these as like software dependencies. So your data components are, the dependencies that your detectors have or your detection analytics have. So without them functioning as they should, your analytics don't work. So MITRE ATT&CK already does a fantastic job of breaking down techniques into their requisite data components. To use our favorite example here of LSAS memory credential dumping, we have our proc-dump example, which breaks down into a few different data components: process creation, process access, file modification data components, etc. So what we did here was we took our data components on the y-axis and looked for commonality between attack techniques. So on the x-axis, you have the percentage of attack techniques, enterprise attack techniques, that have dependencies on these data components. So luckily for us, there's a lot of overlap here, which makes it seem like this problem should be pretty easy if we want to validate data components, with things like command accounting for like 43% of attack techniques. But the problem gets a little bit more complicated because you could just simply start up a Windows server, install a sensor, make some file modifications, start some processes, and make sure they look good and call it a day. But we're kind of all forgetting about that server 2012 cluster or that CentOS 6 server that has all the production data on it that if it gets popped, it's going to be a bad day for everybody. So our testing environment needs to closely match our operating environment as well as we can. So we suggest that the way you go about achieving that is through end-to-end functional testing. So you can read the developer documentation and figure out, so in some cases, like what data components may or may not be available for different OS combinations. Um, but a lot of EDR vendors don't like publicizing that information, and probably rightfully so. That's kind of exposing some of their blind spots. But even if they did, there's going to be software bugs that you might encounter in either in their code or your code. So the best way to go about testing this is through actual functional testing. At least in our experience, that's what we'd like to suggest. So at a high level for functional testing, we're going to spin up some infrastructure, install some sensors, run a functional test. Then we're going to report on the expected results of those tests and compare those expected results to what we actually got from the sensor, and then analyze and detect changes in those results, and also store that for historic use later so we can spot regressions. So what we'd like to give you is a bunch of code you could take home, just plop into your environment and have it work. But the reality of it is, like, I think we all work with different tech stacks, and it's rather complicated and it requires a lot of retooling. So what we'd like to offer you is like how we approach this problem, and how you might think about approaching it in your own environment. So we broke our validation workflow into 3 main steps. We have a spinning up infrastructure, running those tests, and then analyzing the results. So in our spinning up architecture phase, a close colleague of ours, George Allen, is the primary author behind what we call Coal Mine. It has 2 main concerns. The first is spinning up infrastructure, and the second is kicking off or running the tests. So for spinning up infrastructure, we would suggest using infrastructure as code. So what we use is Terraform. That gives us repeatability, so we can easily, continually spin up infrastructure and tear it down. And then we're also using Ansible, for configuration management to install EDR sensors, other test prerequisites. Coal Mine's last concern is running tests. So we'll run things like Atomic Red Team, Atomic Test Harnesses, and then another tool called Vuvuzela, that's an internal tool that we use for validating data components and techniques. So let's take a little closer look at Vuvuzela and that data component validation stage. So at this point, we have a test VM with EDR sensor installed on it. That sensor is making observations about what's happening in the environment. And then we're going to treat it like a black box, because we don't know much about it. But we do have control over the test execution. So Vuvuzela is going to execute a test, make observations about what it did. To stick with our proc dump example, Vuvuzela is going to use introspection to figure out things like the command line, its PID, hashes, etc., that we'll later use for comparing against what we actually got from the EDR sensor. This is kind of like where you can really quickly see potential issues that you might run into that could affect your detection analytics. So, the EDR sensor example here on the left, talks about process paths a little bit differently than how we expected. So if we had detection analytics that relied on C:, like that could make, a bad day for some of those detection analytics, and they may not work at all. We could also have just bad data, as is the case here with like the process PID being off by 1. One really quick thing to mention here too, before I pass it over to Adam, we think it's important to be, there's value in testing the data components in isolation. So just testing things like file modifications to see if your EDR sensor profiles a bunch of different file types. But it's also important to, test using actual adversary tradecraft and techniques, because that's when you kind of get to elicit some really interesting changes in EDR telemetry. One really quick example being parent PID spoofing. You can, through a combination of different API calls, you can manually specify which parent PID your process starts under. A lot of EDR sensors are wise to this, so they'll correctly reparent the process. So it's good to use a combination of both adversarial and kind of data component testing in isolation. At least that's what we found. So the last thing that our test execution phase does is we're going to send like a report to the next stage and give it some information about the test sensor, endpoint, anything that's going to allow this next stage to triangulate and figure out where it should be looking for data. And then we're also going to send a list of those detection analytics that we want to validate and the standardized telemetry. So those are the two parts that we kind of pointed out in the data pipeline. Standardized telemetry is going to help us validate data components, and then detection analytics is going to help us validate that our detection analytics are functioning as they should. So I will pass this over here to Adam.
Okay, thanks, Jesse. Yeah. All right, so we've run our test. All of our sensor data has gone to our production engine, and then the test results get dropped into an S3 bucket, and that's where we start analyzing them. Dropping the data into the S3 bucket triggers our telemetry validation Lambda function. If you're not familiar with Lambda functions, it's just serverless code in AWS. It's a bunch of Python scripts. The first thing they do is they go into our production engine and grab all of the test data associated with that specific test run. So all of our native or raw telemetry, all of our standardized telemetry, and then all of our alerts or our tip-offs. Once we've identified our relevant engine data, we then perform our analysis. And this analysis is less about saying if things look good or bad, and more about just taking a bunch of measurements that we're going to analyze at a later stage. So the first thing we do is something we call telemetry profiling. And the idea is we just go through every single event type, every single field, and just determine what percentage of the time there's actually data in that for the specific source. That's really useful for our detection engineers, where if you're trying to build an analytic and you're looking for a field that isn't actually in this sensor, you're accidentally excluding a large portion of our customer base, which we don't want to do. And so by making taking these real-time measurements of this data and making it available later, we make sure that it's not just institutional knowledge that knows this, it's actually built into our workflows. The next thing we do in the core of this function is that we're comparing our expected results to our engine data. For detection analytics, that's really easy. Detection analytic 1, 2, 3, 4 should fire. We look through our tip-offs. We have detection analytic 1, 2, 3, 4. We're good to go. For standardized telemetry, it gets a little bit messier. We have a list of all the potential fields we could have in a piece of telemetry, which may not match exactly. If there are mismatches, we still want to find the correct piece of telemetry. And it's also possible that the piece of telemetry we're looking for isn't even there. So the approach we've taken to this has a few different steps. So the first most basic thing is we're just comparing field by field. Do the fields match? We call it a valid result. If they don't match, we call it invalid. And then we want to make sure that the piece of telemetry with the largest number of matches is the correct piece of telemetry we're looking for. But there are edge cases we have to deal with here. So the first are things like hashes. So if a piece of sensors will often give us 1 or 2 types of hashes, to say like MD5 and SHA-256, but not SHA-1. And because of these variations, we want to make sure that these matches or these lack of matches don't count against this match. So we'll skip certain tests. The other thing we'll do is we have to weight fields slightly differently. I think a good example is in a process start record. The PID matching is a much more important match than, say, the name of the user that launched the process. So by doing that, we've sort of found a good way to actually make sure that, yes, this seems like the correct piece of telemetry, and then we can report what we think the matches and the not matches are. Next, we take that data, we basically convert it into a bunch of tiny flat JSON records that are easy to search in Splunk. We drop them into an S3 bucket, and that can be accessed through an API, but also it gets forwarded to Splunk. So Splunk is where we do a lot of our analysis of this data. And what I'll say is that I have a number of dashboards we've created. They sort of start at a very high level, let you drill down. But really the power of this is that what you're seeing are those results that we've seen. So at the top, you have all of our valid fields, right? So we have valid, skipped, and invalid. And in each column, we have the specific field name that we're looking for, the value that we expected to find, and then the value we actually found. Valid fields, everything's good to go. Skipped fields, in this case, we're only getting the process MD5. So we just skip the process SHA-1 and SHA-256 to make sure it doesn't count against the match. But then the invalid test, you see our process path and our process PID, the same thing that Jesse mentioned before in our Vuvuzela results, right? So the idea is that, right, for process path, okay, there's a bit of a mismatch, but maybe this is the right data. But for the process PID, this is a really, really important off by 1 error. This is a somewhat contrived example, but that is an actual thing that we have found, where a PID is off by 1, and that would have been really, really hard to find over months and months and months, unless you had some kind of system like this that's looking at this fine-grained level, right? So this has proved really useful for us to find regressions in data or problems with either the sensors or our own systems. The next thing we did is we slapped on what we call our validation APIs. And this is just an AWS API gateway where you hit different endpoints, they'll trigger Lambda functions to do different things to interact with this system. So we wanted to make this more actionable, sort of easier for us to use, easier for people across the company to use. And each of these endpoints does something slightly different, right? Coal mine launcher, you can launch and monitor the status of coal mine jobs. The Vuzela results, you can look at the analysis results or even submit your own results from a manual run. And then we have our telemetry profiling data, which now allows our people who build our detection analytics to query this and understand, right, what data is available from where. So the final thing we want to talk about are lessons learned and things we thought were interesting and wanted to share with folks. So we have more, we're happy to talk about it at a later time, but for the sake of time here, we have two main telemetry quirks that we've seen a lot of. So the first thing is that the signal to noise ratio is very different for each sensor. The way I just sort of think about it is that higher quality telemetry types are never filtered out. Things like process starts, module loads are always going to be really good, but there's a lot of lower quality telemetry, things like file mods and reg mods that are really, really noisy and are only going to be interesting some very, very small percentage of the time. So a lot of this can be highly filtered, but the way it's filtered is different depending on the sensor. So a good example for file mod filtering, we've seen one sensor that actually filters by the number of file mods a process will make. So if it starts generating too many file mods, it'll slowly filter it out, and then at some point it'll just stop showing them altogether. But for the most part, this filtering really comes down to the directory and the file type. And I think a good way of describing it is on Linux, everything is a file. File mods can get really, really messy. So take a text file and drop it into temp. That is a very uninteresting action because nothing is going to happen with the operating system. But if you drop a text file into /etc, you're going to change the configuration of the operating system potentially. So that is very, very interesting. So part of this is, right, file type and directory, but then other file types like shell scripts, Python scripts, executables, that's always going to show up. And really the important thing for this is that, right, when you're dealing with a telemetry source, you have to kind of explore these edge cases. This was a lot of generating a bunch of results and me just like pounding away at the keyboard, trying to figure out what these patterns were. But when you understand these edge cases, you'll then understand, right, what you can detect and what you can't detect from certain sources. The next thing is that file telemetry has very inconsistent meaning and terminology. So if you philosophically think about what a file mod is, you're calling some sort of a system API that's opening up a handle to a file that's going to modify the index of the hard drive to then point to the part of the hard drive where you're actually going to write the contents. And there's all these different places that you can hook, and often the EDR sensors will hook different places. So I have one where you create a file, and actually generates 3 separate file create records with slightly different pieces of information. The reason why this is important is that you really need to understand the difference between, like, what is a file creation, what is a file modification. So, right, if you're looking at, I want to find where this piece of malware was dropped to disk. Well, is the file creation, you want a file creation where there's a hash? Or is the file creation really creating sort of like the infrastructure to then point to that place where you're then going to write the contents, and that is a separate file modification. So it's understanding kind of the inconsistencies of individual sort of telemetry types like this, and other ones you might see where it's not exactly what you expect it to be. So next, I want to talk about some of the challenges of using EDR telemetry, right? And this is kind of, right, the thing I've sort of hit on a few times already, is that the level of detail is limited. More traditional types of behavioral analytics like API calls, you're not really going to be able to see that in EDR telemetry. Same things with static binary signatures outside of a hash. So, right, if you know this piece of malware always has these 300 bytes in a row, if they recompile the file, the hash is going to change. So from EDR telemetry, it looks completely different, but that static binary signature that would work isn't going to work on this telemetry. And then certain telemetry types are limited because they're noisy. I mentioned file opens before, and that's because a few months ago, I was asked to look into sort of credential theft. What are the things we're potentially getting from our EDR sensors that we're not standardizing? And the answer is not a lot. So for dumping LSAS, we do get really good telemetry. Ultimately, that's going to turn into a cross-proc because we need to access LSAS memory. That's a really high-quality signal. There's all the other stuff I showed before, but that's a really core one. But what about things like application credential theft? Think browsers, password managers, that type of thing. You're really not going to get very much telemetry because it's just the wrong process opening the wrong file. So you get into that case where file open telemetry is not interesting unless it's really, really interesting over here. So the good news, though, is that EDR sensors are very good at generating alerts for this type of activity. For EDR sensors, right, you're getting a much richer data set, but you are limited in terms of the number of analytics you can run and the complexities of these analytics, because you're limited by the compute of an individual endpoint, right? Potentially an individual laptop. On the other hand, when we go to some of the benefits of using EDR telemetry, the good thing is that you're offloading these detections from the endpoint. So it's a less rich data set, but now you're limited not by the compute of a laptop, but by the compute of AWS, which is big. So it's very highly scalable. Another kind of strategic advantage you get from this is that adversaries can't see alerts. So if you have an adversary who's sophisticated enough to study the security products they're looking at, if you look at an EDR sensor, they're going to be like, hey, I did this thing, that generated an alert, therefore maybe I shouldn't do that. However, even if you can see the EDR telemetry that's being generated, the adversary won't be able to see, well, I made these 5 pieces of telemetry, that triggered this detection analytic, right? So by removing the analytics from the endpoint, you have a strategic advantage over the adversary. And then finally, EDR telemetry provides a very versatile representation of behavior. I think it does a really good job of capturing the context of what's going on and correlating things. So you're not just getting an alert triggered, a bad thing happened. It's like, well, a process did a bad thing. Now let's use process start records to reconstruct the process tree. Let's grab all the pieces of telemetry associated with each process and kind of give you a picture of the behavior that happened that triggered this activity. So just to go over key takeaways we wanted to say. So right, EDR telemetry by definition balances signal to noise ratio. So you need to study those edge cases to understand the sort of where the problems are. And I think that applies to a lot of telemetry sources you can deal with. So validating a technique coverage using data components scales really well, right? Once you understand the base data components, you can kind of reconstruct them into whatever attack technique you need to, but know that you're going to have those underlying data sources. Providing end-to-end functional testing, it provides a really clear signal when there's a problem. It doesn't always show you exactly where it is, but it's like, hey, the PID's off, we should really look into that, and then you can dig into it. It also captures a lot of the nuances of techniques that you get from a more contrived scenario that isn't trying to emulate the adversary tradecraft. Automation allows us to scale this really nicely across lots of sensors and operating systems. Right, the con is just that the telemetry is limited, but the pro is that you are offloading the telemetry and your detections from your endpoints. It provides a lot of context around your alerts. That's all we have. We started a blog series called The Validated Canary with links here. We are trying to dig into this in a whole lot more detail, but we're also happy to answer questions either now or later to sort of give you the tools that you might want if you want to try to reconstruct this yourself. We're happy to talk about as much as you want. So, thank you.
Excellent presentation. And in the spirit of bird analogies, I come bearing a potential dove of peace, maybe to settle the Mishta versus whatever stew of letters you send. Drama, maybe we just use a technique ID. T1218, ordinal 5. Right, soft landing place. So I know we have time. We probably don't have time for audience questions, but I'd have a quick one. You outlined some really great ideas in terms of how to actually see that detection pipeline, from soup to nuts. Sampling your sensors, threat modeling, all these ideas. What is your advice on just getting started? I think you mentioned some really good ideas for scale and automation, getting really complex. But like for maybe smaller shops that are just starting to get the wheels turning, what's some guidance you can share there?
Do you want to take that?
Sure. I always kind of fall back to Atomic Red Team and Atomic Test Harnesses. I feel like those are great places to get started. And then kind of look at what data components are used in combination to build your detection analytics. And then just look at the data too. Kind of just go splunking through the data, figure out what it looks like, and maybe read some documentation too. But I always kind of fall back to Atomic Red Team, Atomic Test Harnesses.
Yeah, start small. And I like the way you kind of translated that to look at those components. And again, the way we did structure those was to be that soft landing place of being maybe a little bit abstract, maybe not as clear, but also something that's a little bit understandable. So open invitation, if you ever have feedback or contributions, or we're even getting notes today, our defensive team is nerding out on these talks. So thank you so much. But small token of our appreciation just for you. Thank you so much.
Thank you very much. And actually, we did open source our coal mine role, Ansible role to run Atomic Red Team tests. So that's a good place to start. If you spin up your own EC2 instances or wherever they are, you can use Ansible to do that. So yeah, right, Atomic Red Team and Atomic Test Harnesses are great to start up.
Gotta love automation. Thank you.